Alright, so let's back to the lecture. I'll still continue a little bit faster from next week. And the next week I'm going to still talking probability and slowly move to the structure reliability area. Okay, then I have to talk also probability in there because it's all base is probability theory, but not difficult probability theory. So we're gonna bring the probability theory as need arises. Okay, we are not going to just learn the probability, but going into structure reliability, then as we need, I'll just bring back the probability theory that we need. Okay, so model is concerned, the probability model is concerned. How many did you learn? Only one, normal distribution, which is widely used distribution and also very popular distribution. There are lots of physical phenomena that you can use the Gaussian distribution. Same, normal and Gaussian. And still the one in this moment, one random the variable. Sometimes you have an equation set. Sometimes something like y is equal to simply x. Then that situation is very simple. Or x squared. Lots of the functional relation between the x and y. That's what you learn in algebra. And question generally, I can say y is equal to the gx. Okay, functional relation between x and y. Then let's say x and y, both are the random variable. And I know x have fx. So we know the probability distribution function or probability density function of x. And x and y has a functional relationship. Then the question is, what is the probability density function of y? Okay. How to find about the y probability density function? That's the question. So that's what we're going to learn a little bit. First, I'm going to assume that this is called, there are different methods to find the probability density function of y, but I'm going to use the so-called the change of the variable. Change of variable approach. Because very straightforward. So I'm going to say x or capital X is really same class of the variable. Capital X is random variable. X is the value of random variable for the particular outcome. So I'm going to say X is real single continuous function. And y is also real single valued. It's a valued continuous function. Let's say it has a one-to-one relation. For the one value of x, you have one value of y. It's real and it's continuous. That assumptions. Okay. Then question we are looking for is Fy. So you will start always starting from the definition. Definition of probability density function of y. Okay. So definition is a limit delta y goes to 0. Then probability such that now random variable is y plus delta y over delta y. Okay, it's a definition, right? It's like a slope of probability distribution function right at the point of y. Slope, right? Delta y is approaching to 0. Clear. I can rewrite this is a probability such that capital Y belong to the y and y plus delta y. So I'm going to rewrite this basic definition as a limit goes to 0, but I am going to change this expression, probability expression, as x Can I do that? Can I do that? Why not? Because this is a real single valued function. So you can do that. For probability, x and y has a one-to-one relationship. So in addition, I'm going to employ this. I have to do this. I'm going to move delta y right there. Delta x, so it cancels out each other, so it's no change. It's not the magic, but it's pretty good, isn't it? So if you look at this carefully here, and this is the definition of probability density function of x. So this is a probability density function of x, this guy. And this probability density function has to be greater or equal to 0, right? It's always a positive probability density functions, right? It's amplitude of graph, right? And this guy, when you take a limit, delta x and delta y approach to 0, then this will approach to what? Dx, dy, isn't it? So dx, dy this can never be negative. Why? Because this guy has to be the positive. Probability density function has to be the greater or equal to 0. So I can say, okay, I can put, to make sure there's a positive value. So I'm going to add so Fy y is this. So you can determine the probability density function of y when you know the functional relation between x and y by like y is equal to function g of x. But condition was here is a real single valued continuous function. So this is a typical relation to get the Fy. But what happens, sometimes you have a multiple kind of the information. As I wrote there, y is equal to x squared, which is like this, x. For the y, given y, it has multiple number of value. The relation between x and y are multiple. Two roots, x1, x2 exist. What do you do? Okay, in such a situation. So for that situation, if y is many to one function of x. Now expanding the one from one to one relation, I said y is many to one function f of x, then I can say gx may be inverted. In each case, for each case, if it has a two root, then you end up having the two cases. Then you have to add together like this. Fy is equal to, if I express using probability distribution function, I can generally say here something like this. Implication of terms is within the capital Fy. Then we learned this, fx xi is dx over dy. So I'm going to rewrite this because using the inverse of the function. So inverse of the function, y is equal to x squared. So this is like gx, no trick, very straight manipulation. So if I invert x is equal to, mathematically, I can write just like that, okay? Inverse of g function. And in this case, x is equal to plus minus square root of the y. Then here I can write x1 is, let's say, plus y. x2 is equal to minus y. And here, this is equal to, I'm not sure I can say, this is equal to g1 minus 1y. If I have to express, this is equal to g2 minus 1y. If I just to write the notation correctly. Okay, can you see? This is simply x1, x2, two roots. In this case, I said this is x1 or x, so positive is 1, doesn't make any difference. Negative is x2. Just to follow the... So if you do that, so now I can write fy, y is equal to fx, x1 dx over dy, but x is, using the notation, the inverse function. So this x is, I can say, g to the minus 1 y. So this is the x is fx. This is if I just write over here, this is fx x1 dg1 inverse y over dy. So nothing to confuse. It's just a notation. I just try to match the notation of y with respect to x. That's all I set this up. No engineering. It's straightforward, simple manipulations here. And this is that. So I'm going to plus fx. Now it's x2. We're going to manipulate for each case. It has x1, x2. Then you anticipate the two term. And this is equal to dg2 minus 1y over dy. So this term is x2. Just to try to make the functional relation using simple example problem x squared, which is a 2 to 1 function. I'm going to just continue, make it simpler, a little bit simpler from here. So if I just rewrite, you can rewrite down here. So far, no problem, right? So now I'm going to just continue. This is two terms, of course, and x1, and this is d square root of y over dx. That's x1. Okay. This is x1, but I have to express y because we are looking for the PDF of the random variable y. Okay. And plus fx x2 minus d square root of y dy. And this is equal to, I'm just solving for the case y is equal to x2 function. And you rewrite here x1 and the square root, you have to differentiate square root of y with respect to the y. If you do that, that's a half y half that plus fx x2. Of course, if you're gonna rewrite in terms of the y, this x2 is equal to g2 y. Okay. So then now is minus half y minus half. This is end of it. But if I say, okay, well, this is fy, well, usually the Gaussian distribution is a very popular distribution. So I'm going to say that, let's assume let x is equal to the standard, we learned the standard, the normal distribution function, which has zero mean and the standard deviation is 1, right? So if I want to say let fx is equal to 1 over 2 pi e to the minus 1 over x squared over 2. Have you seen this before? Have you seen this? Of course, the other day we introduced standard Gaussian probability density function. If I'm going to say let fx, because it's very popular, then you can fit this guy right into here for x1 or x2. It's a little bit trickier in this system, but it's still very, so just to substitute 1 over 2 pi exponential function and minus half of this sigma y whole thing, because this is x1. That's x1. Half of y minus half. Looks like very lengthy, but if you look at carefully, it's not much in it. And what's this? And plus another term is 2 pi exponential function is equal to minus y square and absolute minus 1/2 y minus 1 over 2. So this term is identical to that term because it's absolute. And this square is y square. I'm sorry, this is simply y. And this is identical. So eventually what you see here is first term is identical to the second term. So what you can find here is equal to 1 over square root of 2 pi exponential function, okay, minus 1/2 y. It is wrong. Then I'm going to multiply 2 here and 1/2 y minus half. Or, well, I think this is end of it, isn't it? So this is equal to twice fx, x is dx over dy. Can I do that? So back down to very simple, but there is a one assumption left. What's the assumption? Fx is Gaussian, standard form of Gaussian density function. So this is equal Fy, y. So you have in such a nice relationship. So if you look at some book, they go straight to here for 2-to-1 functional relation between x and y, but you have to be careful. Implication is the normal distribution assumption, which is really somewhat popular. Okay? Change of the variable. You can look at this in the reliability-based structure design book, red cover, in the beginning, around the page 15 or 20, but just one line. It shows just one line. Behind the story is like this. I just did it. Okay. Question? Straightforward. And if I say I will cover everything on the probability model, basic probability theory in 2 weeks, that's a total lie. I didn't say that, but we'll cover, get the basic idea. Most of you took the probability course, but some of you didn't. I assume you know much of this, so that's what I am doing. Yeah. Y is 3 to 1 function? Yeah, 3 terms.
3 to 1 function.
Yeah.
Then fy has multiple 2. Can we change to 3?
This should be 3, but distribution is Gaussian distribution. Assumption is in behind. Yeah, it's a 3. Then you have to, yeah. So usually you can say the n rather than 2 or 3. Okay. But remember, this is the summation of the terms, right? If you have 10 to 1 relation, then you expect to total 10 terms in general. Then you have to work out, right? So, then sometimes, well, in this case, it's one functional relation between the y and x. But sometimes you will face like this. You will face like this, like x1, x2, xn are independent random variable. What does it mean? You heard now first time independent random variable. Some of you took the probability course. What does it mean independent?
There is no relationship between that variable.
It's a bachelor state. Didn't get married yet. No relation, right? Just a friend, right? So no relation at all. Yesul is an independent random variable. And everybody here is an independent random variable except myself and Yonghyun has a baby. So he is not independent random variable. So independent means statistically independent. It looks not as Yesu goes out, nobody can say, oh, she's single, right? But statistically, as you open her heart, oh, she's really single. And open Yonghyun's heart, oh, he has one nice child, Then there's a dependent variable. Independent means statistically independent, okay, property-wise. So still goes up, independent random variable, okay? And also, all this term has any probability density function. Any. Doesn't have to be normal distribution, can be any probability density functions, okay? Then, question arises as x1 plus x2 plus all the way through xn. Question is, what's the probability density function? As n goes approach to infinity. Approach, okay? Not infinity. You can't define the infinity. Then answer says, theorem says, it follows the normal distribution function. It's called central limit theorem. Got it? Central limit theorem. If you want to learn more on the central limit theorem, you just go into internet, type central limit theorem. You have a beautiful Wikipedia, informations and all that. So that's why normal distribution is widely used. If it has a many terms, I don't care what the probability density function each random variable follow. Beauty is its approach to the normal distributions. Central limit theorem. Okay, I'll stop here. And as I mentioned, if you have some nice the data fit into the normal distribution or any probability distribution, send it to me. I'll just look at and keep it as a good example. I'll see you on Monday.